Good afternoon. It's Friday, September the 27th, and I'd like to take some time in this video to walk through Chapter 5, the normal curve. And these are a couple of images we'll get to here in a few minutes, but there's some recollection, some remembering that we need to do before we get into this. One is that we go back to Chapter 2. I want you to, if you want to go back and look at some point, remember that there are visuals there that are bar charts, where we have vertical bars that represent counts of data within each bar. A higher bar, there's more frequency or more counts. A lower bar, there's less frequency or less counts of whatever it is, apples or whatever it might be. So I want you to recall those bar charts. And then I want you to imagine, if you were to go back to Chapter 2 and take a light leaded pencil and draw a line, dot to dot, from the top of a bar to the next bar to the next bar to the next bar. And what you'll be doing at that point is drawing a curve, like these. The difference there might be that they're not normal. A normal curve is symmetrical, so that it's centered on the mean, and 50% of the distribution is to the left, and 50% of the distribution is to the right. And it's an important point to remember. But you always want to remember, when you see these curves, that they are really dot to dots. And implied in the background of a curve like this is a bar chart, much like in Chapter 2, where you would go and you draw that line from top of the bar to the next bar and all of that. And you'll get something like a curve. Now, hardly ever do you get something that's absolutely normal. This is kind of an abstract concept. Most bar charts, most distributions are not absolutely centered on the mean, with 50% above the mean and 50% below the mean. You remember another element of central tendency and Chapter 4, dispersion, skewed. If it's normal distribution, it's symmetrical, but if there are higher values on the right-hand side and the upper value, then it's pulled to the right and becomes skewed, positively skewed, which would mean that a lot more than half would be below that mean. Or if the has an extra number of low values on the left, then it would have a negative skew to the left, which would mean that most of the, quite a large number, far more than 50% of the values, are off to the right. So when things are lined up properly, which they seldom are, but we assume normalcy in most cases. Normalcy, the mean is in the center. There's no skew. It's normal. The mean and the median sit right on top of one another. So that's an important concept to keep in mind. The other thing to keep in mind from Chapter 4 is to remember that standard deviations have an index of difference or diversity or variation. You'll recall that in Chapter 3 we collapse the data to a central value using continuous variables in illustration here, that we collapse it to the mean or the median, which is the geographic center of the distribution regardless of what happens to the mean being pulled one way or the other. But here we're assuming they're both in the same place. So when we collapse it to the center, we miss all that variation. And we talked about this. We missed all that variation of all of the x's that are above the mean and below the mean. We miss all the variations between, or the amount of variation between the x's, or amount of variation between the means and all the x's, and all of that. And Chapter 4 was, the standard deviation was a way to capture the values that deviate from the mean. Those that are higher than the mean deviate to the right, and those that are lower than the mean, the x's I mean, they deviate to the left. And then what that standard deviation does, it standardizes those and gives a kind of a constant value as you move to the left or right. You'll see that here in a second. But to remember that a standard deviation is an index of variation, such that if you have a standard deviation larger than another, then the standard deviation that's larger than the other indicates that there is more distribution in that distribution. There's more variation in that distribution than in the other one. So the larger the standard deviation, the more the variation that there is. And we can another way you can demonstrate that is like in the range. If you subtract your low value from your high value and you get 20, and then on another distribution you subtract the low value from the high value and you get 43, then that tells you right away there's more variation in the distribution where the range is larger than where the range is narrower. But there again, in the range, we don't have any information about what's going on between the low and the high value. So the neat thing about standard deviation is it gives us a chance to capture all of the information having to do with variation around the mean. Okay, now when we do these normal curves, the vertical lines are the standard deviations. Now, if you look at, I'll lean over here. If you look at the illustration figures 5.1 and 5.2 on page 116, you've got IQ for males and IQ for females. I don't know whether this is actual stuff or it's just some kind of abstract, and why they would pick IQ as opposed to weight or something, I have no idea. But anyway, when you look at this, you can see that there is greater diversity or variation around in the males because the curve is sloped out wider. So the range is wider. And if you look at the tail of the curve on the left and the tail of the curve on the right, it varies between something below 40 to something above 160. If you look at the range in figure point 2 for females, that range varies somewhere between 68 and about 132. So there you can see that the diversity among, or variation among women is less than the variation among men. Those vertical lines are the standard deviations. So in a way, when you look at those shapes like that, we're really talking about the geography of the curve, because you'll notice that those vertical lines have varying widths of space. If you look at 5.1, the space between the center line and the next one to either left or right is much wider than the space in the center line of the figure 5.2 and the line either to the left or the right. That indicates spatially or geographically that the standard deviation for women is smaller than the standard deviation for men. In other words, women, there's less variation around the mean, and for men there's more variation around the mean. So there you get a sense of where we're going with this. These are pictorial images of a distribution measured by standard deviations. The broader the shape, the greater the standard deviation. The narrower the shape, the smaller the standard deviation. Always assuming here, as you'll see, no matter what the shape is, whether they're heaped in the middle or spread out, it's centered on the mean so that anything to the left of the mean is 50% of the distribution, and anything to the right of the mean is also 50% of the distribution. Now there's another interesting issue that comes from this, and you'll see that on page 117 and figure 5.3. No matter how wide the distribution, no matter how wide then is the standard deviation, no matter how wide is the normalcy of the curve, those numbers of values, the values that range between the first standard deviation and the first standard deviation either side of the mean, always encloses 68% of the distribution. So if we go back and we look at figures 5.1 and 5.2, you see that first vertical line either side of the mean is the one in the center. Either side of the mean, then each of those two vertical lines for males and the two vertical lines for the females enclose 68% of the distribution. It's always the case. And then as you look at figure 5.3, you go out to two standard deviations, that always encloses approximately 95% of the distribution. And if you go on out to the third standard deviation either way, that encloses almost nearly 99% or over 99% of the distribution. It doesn't matter whether we're talking about weight of apples or IQ or height or anything that is continuous. If it's in the distribution, any variable that is continuous, if it's large enough, something over 100, maybe up to 1,000 or more, it'll take a normal shape, and whether it's apples or oranges, numbers of leaves and trees, whatever it is, 68% of the distribution will be between plus or minus 1. Deviation, 95% will be plus or minus 2, and 99% plus or minus 3. It's a principle, a constant through all of this. And you'll see as this is the groundwork. This is a transition chapter between the more descriptive stuff we've been doing with chapters 1, 2, 3, and 4. Next week we'll be moving, or after the exam, which we'll talk about here in a second. When we get to chapter 6 and 7, we're moving into inferential statistics, another level of statistics and descriptive. And these curves will become central to our being able to interpret what we're capturing in our sample is a good estimate of what we would like to have captured in the population. All right, so keep that in mind. Now we have another curious thing that's going on here, which is kind of interesting. Let me get off the stool here. Maybe I can do a little bit of illustration. These are the standard deviations here. This is kind of an illustration of what we were talking about a minute ago from those figures in the front. So I'm going to erase this. You can see the 68, 95, and 99. A wider normal curve, a narrower normal curve, suggesting differences in standard deviations and all of that. So if we were to draw a single one out here, let's call this a normal curve, and to reinforce that it's a normal curve, we have the mean and the median in the center of it. Here's the high value out here, and here's the low value. And then we have the standard deviations that have broken that distribution down into standard sizes, 1, 2, and 3, 1, 2, and 3. And remember, this is 50% here, and this is 50% here. The other thing we want to keep in mind is anything to the right of the mean, if we were to subtract the mean from it, we've demonstrated that to ourselves in the last couple of chapters. This is the plus side. Any x that we subtract the mean from on this side is going to be plus because all the x's over here are larger. This is the negative side, so any x's here, if we subtract the mean from any of those x's, since they're smaller than the mean, will be a negative value. Negative skew, positive skew, reinforcing all the concepts that move forward with us as we continue our journey through statistics. Now, what we're going to talk about is z-scores. The z-score equals the xi minus the x bar over the standard deviation. Now, there are going to be some circumstances in statistics, which you'll appreciate, that where the data are given to you by Healey for you to do the calculations to solve the problems. For example, if you're out there in the world, you would have to calculate out the mean of chapter 3, say, in this distribution, and then you'd have to calculate out the standard deviation of the distribution before you could even get to the z-score. So the convenience of Healey at this point is they're giving you the mean and giving you the standard deviation. We can be grateful for that, can we not? So how we get the z-score is using this formula, and it's the formula on page formula 5.1 on page 118. Now the interesting thing about the z is the z, I'm trying to make that come out right, equals a standard deviation. Now I should say it equals a deviation, would probably be a better way to say it. These are the standard deviations, but there are other deviations that occur. There may be deviations where there's an x that lies here between the mean and the first standard deviation. There may be an x there. And we want to know how much of this total distribution is accounted for between that x and the mean, or between an x out here and the mean, or an x down here and the mean, or two x's on the left-hand side, or two x's on the right-hand side, or the difference between how much of the distribution is caught in percentages between an x on the bottom side and an x on the top side. Two x's here, two x's here, two x's like this. It's a way of looking at the percentage of the distribution that lies between any two x's, is how we do this. So when we do the z-score, for example, if we do a z and we get a z, let's say we do something, and this is hypothetical. Let's say that we do an x minus an x bar, and we get a z-score of 1.50. That is a deviation. That is a point in the distribution of deviations here where that particular value, let's call x equals 43. So then, in that case, we would find x43, 1.5, is halfway between the first deviation and the second deviation. 1.5 would be about right here. So the z of 1.5 would be here, and so would the score of 43. So it gives us a way, the z-scores do, of finding out where in this distribution of this curve lies or resides, or is situated or located, the value of 43. Now you think that's kind of interesting, but even more interesting, once we know that, and let's say we know that this is 50%, and let's say that between here and here we find out is 20% of the distribution, then we know everything from 43 below, 70% of the distribution lies below 43. 70 from 100 means that 30% lies above 43. So you can see very quickly, not only does it give us the location, but it gives us a way to see where that location is in relation to everybody, all the other x's, everybody else in the distribution. So z is very helpful in that sense. Takes the standard deviation issue a little bit farther, gives us some practicality where we can explore distribution, the content or the variation of the distribution to get some very interesting information here. Let's take a look at the book. I'm going to switch back over here to the bench or the stool. Now, there are some ways that we can, that Healey or statisticians provide us for calculating out percentages and proportions between a mean and an x, and then from there being able to calculate out any differences from one x to another, or an x to the end, or x to the tail left-hand side, and all of that. And you'll see in table 5.1 is an illustration of how to find areas under the normal curve. For example, let's just take a look at the left-hand column there, A, where the z is. If we find a z of 1, right, then that means that the z of 1, which happens to be coincidentally with our standard deviation here, the z of 1 has between it, if you look at column B, has between it and the mean 0.34, about 34%. And then we go back and say, oh, we just said that between the first standard deviations either side, 68% of the distribution lies. So here we have demonstrated to us in this table that between the first standard deviation and the mean is half of that, 34%. And then if we look at column C, it tells us how much of the, once we get this, how much of the distribution remains beyond C, or beyond B. So then, once we have that, then that means if we look at column C, roughly 15.87% lie to the right of standard deviation 1. So very quickly with this table, we can see what percentages between the standard deviation or the z and the mean, and how much lies beyond it. Column A gives us the location. Column B gives us the amount of percentage of the distribution between that particular z and the mean, and then column C tells us how much is beyond B. Now, one thing we have to keep in mind, this is symmetrical. So you won't find in this table, we'll look at Appendix A here in a second, you won't find any negative values in columns A, B, and C, because the idea is since this is symmetrical, if whatever the difference is between the percentage distribution between the plus standard deviation and the mean is going to be exactly the same as that between the minus standard deviation of 1 and the mean. If this were minus 1.50 instead of 1.50 and it was down here somewhere, the same amount of geography or proportion of the distribution would lie between here and this mean as between here and this mean. Because it's symmetrical, all we have to have is a positive table, if you will, and then we just have to remember that those values also apply to the left-hand side of the distribution, or the negative. And when it's over here and it says beyond the mean, or beyond A, when you're doing column C, beyond on the left-hand side is down to the tail. Column C on the right-hand side of the distribution is out to the right-hand tail. Column C again on the left hand is out to the far left-hand tail. So that's a tricky business. You have to keep that in mind. And one of the things I'm going to ask you to do, and you look at the homework which is posted, draw your turtles. Now, you probably, if you'd already seen this, said, what the blazes a turtle have to do with this? It's not biology class, right? This is a turtle. This normal curve with the standard deviations, those are stripes on the back of the turtle, and then you're going to draw in vertical lines what you find when you do your z calculations. You're going to put your lines there, maybe dot it or color them in some way, shade them, so that you can see visually where is the distribution of your interest. Above that, below that, all the way below that, all the way above it, wherever it is, draw your turtles. And you may think, well, I don't think I really need to do that, but I can tell you this, I think you really do need to do that, because once you start doing this, it's very easy, since this is symmetrical, to think you're on one side when you're really on the other. So the more you visualize this, I think you'll find the homework much better. And I will speak sternly to you if you do not put your turtles in there, particularly if you get the wrong answer. So draw your turtles. The turtles is the normal curve with the normal standard deviations drawn on it, and then the applications of the z-score, where you're going to put those and how you're going to shade it in so that you can visualize the area of the normal curve and distribution that you're interested in. So keep that in mind. All right. If you flip over, I don't know if it has a page, but over here there's Appendix A, 453 it looks like. You'll see that there is quite a table there of area under the normal curve. You can see the z-scores start at 0.00 and go for 3 or 4 pages all the way over to the back to 3.10 and keep going to 4.0 and all that. And you'll notice that once they get up to about 3.50, they become about the same. And that's only because as you get out here to the tail, the increments get smaller and smaller and smaller because there's less and less and less and less and less and less in the tail. So once you get out here a little ways, the distribution, the content of the distribution, the numbers of cases of frequency in the distribution is so minuscule that, theoretically speaking, that the z-score takes on, just it continues like into infinity. All right, so now let's take a look at 5.4 on page 120, finding the z. You'll see on these 2 pages, see up in the upper right hand or up the top of 121, an example of a turtle without the standard deviations, but you want the standard deviations so that you can see where do I put my 1 point. If you don't have 1, 2, and 3, where are you going to put 1.5 or 2.3 or 3.6 or 0.82? Where are you going to stick them? So put your vertical standard deviations in there to give you some positional visualization of where to plot out your z-scores. It's very important to do that. Okay, you'll see here is an illustration of how they found the z-score. Here you can see in the formula there in 5.4 on the bottom of 120 more or less. You see the formula, and then you see somebody's got a score of 117, and then the average is 100, and the standard deviation is 20. So you subtract 100 from 117, you get 17, divide that by 20, and you get a plus 0.85, which means that the 0.85 is not quite to this standard deviation. So we're looking at an area right here. So 0.85. So then, if we were to go to the Appendix A and go till we find 0.85, you'll see that the area between, in column B, for 0.85 is 0.3023. So that tells us about 30% of the variation is between the 117, which is 0.85 is the location on the distribution, but it represents the value of x of 117. So that means that 30% of the distribution lies between 117 and the mean. And if that's 30%, that means that this 50% plus that 30%, 80% of the distribution lies from 117 to below. And you take 80% from 100, that means 20% lies above. So you begin to get the picture of how this sort of thing works. And you can see in that turtle they have in 5.4, 30.23 between 0.085 or 0.085, and the mean is 30%, and below that is 50. So about 80% lies below the score of 117. Here you can see that I think probably the best way is for you just to I think the illustrations here are very clear. I don't want to take your time and walk through all of these. I think you can see the illustration as we go through it. One of these is like, for example, right above the table, one step at a time, 121. There, if we go over the next, no, they didn't do it over the next page, but you can see that there is a z-score of minus 1.35. Oh, well, here it is, yeah. You see that the x is 73. Well, that's less than 100. So that when you subtract 100 from 73, and then you've got, that is a minus 27. They should have put a minus 27 instead of just a plain 27. So keep in mind, even Healey once in a while, like all of us, makes an error. So that's a minus 27 divided by 20. It's a minus 135, which means that that z-score is a minus 135. It's about 1 1/3 way here towards the second deviation. It'd be about right here. And you can see that representation on the next page. And here where the question is, well, how many score below 73? So if it's right here, and this says they have it over here, 0.0885, or about 9%. So if this is 9%, that means about 9% of the distribution of IQ scores lies below, and about 91% lies above. And you can see that they drew the turtle to give themselves, shall we say, spatial or geographic reference. Very important to do. If you don't do that, you might draw it over here. And of course, that'd be wrong. So when you're doing minus signs, lay your distribution or your vertical lines of your z-score on the left-hand side. Keep yourself oriented to space. It's not necessarily about time, but certainly oriented to space. Now, finding the areas between two scores, they have a really good table, 5.3. When you find the area between two scores, there's two ways. If they're on the same side, I'll find my eraser here. If they're on the same side, then you take the distribution, take the z. This to work here. Take the z distribution that is large. I'll just designate it that way, and subtract it from the z distribution that is small. So, for example, if find my red marker out here. I guess this is it. If ZL is here, and this is ZL goes this way, and Z small is here, this would be Z small, then what we're after is the difference between these two here. This is that location. This whole thing is the large location, so we subtract the percentages that we would get from column B. We would subtract Z column B from Z small column B, and subtract this B small b from the large B, that's column B in the appendix, and the difference would be the amount that's in between. So that would be a fairly straightforward representation. You'll see they've got a table 5.3 that allow you to take a look at that. The other thing the other way that it works is if you're wanting to look at the amount between two z-scores that are on different sides of the mean. If they're on the same sides of the mean, whether on the left-hand side or the right side, you subtract the larger or the smaller ZA, or column B rather, the smaller column B percentage distribution from the larger, and what you get as a remainder is the amount of difference between them. If you want to find out, for example, how much lies between two z-scores on opposite side, maybe we have an x here and an x here, and what we want to know is this. Then what we do there is we simply take column B for this one and add it to the column B for that one. And then when you add the two column B's, then you get the total amount of variation that lies between the two x's. So if they're on the same side, you subtract the smaller distribution, the smaller B value from the larger B value. If they're on opposite sides, in order to find the amount between them, you simply add the column B value of one to the column B value of the other, sum that up, and that's the total that you get. So I think that's pretty good for covering this for now. There is some issues at the end about probability, and basically, and we'll talk more about that as we get into the next chapter. But let's just say that this value here is at point, if we summed all this up, let's say that this is 80% of the distribution lies this way. Proportionally, that's 0.80. Another way to look at that is, call this a population. Out of a population of 100, 80 out of 100 of these will be, 80 out of every 100 people you encounter, if we put it that way in probability, will score in this range. 20 out of every 100 will score in this range. So, like we had talked earlier in the semester, when we're doing proportions, we can go either way. Multiply them times 100 and call them percentages, something we're comfortable with and familiar with, or we can simply leave them like this and recast it as a probability. 8 out of 10, 80 out of 100, and that sort of thing. So what are the odds of encountering somebody in this distribution like that? 8 out of every 10 people will represent this group. So probability, but we'll talk a lot more about this in chapter 6 and 7 and kind of nail that down a little more tightly than we are this afternoon. You can read that piece at the end of chapter 5 to kind of get yourself familiar with it. Okay, I think that's pretty much what I have to say about that. Coming up in, we're going to have homework 6, but it's been, you'll see, I think, if you've been to Blackboard, it's now due on October the 8th. We've got an exam between, once we finish this chapter 5, then we're going to interval of an exam, homework exam 2, before we move on to chapter 6 and 7. Now, the way I'll do this is on Thursday or Friday of next week, I'm going to do a video that will walk us through, the homework will be on chapters 3, 4, and 5. We'll walk us through a review of 3, 4, and 5 video, post that on Friday, and then I will put an exam up on Blackboard. You'll have 75 minutes to do it, any 75 minutes that you want to do it, between the time I get it up there, probably sometime around noon on Friday, until midnight on Tuesday, say. It'll be a multiple choice exam, and I'll get all that set up, and I'll talk about it in the review video next week. So, I don't know when you're going to watch this, but this video in front of you now, or that I'm doing, but it's Friday afternoon, and chance of rain coming up. Looks like pretty good weather, a cooling trend slightly, so that's a good thing. So weekend coming up, you all be safe out there, and talk to you next week.